Okay, good morning, everyone. It's a great pleasure and honor for me to be with you and talk about distributed optical fiber sensing technology. That is basically a new way to sense things with optical fiber that has revolutionized a lot of different field of application till now. And I think that by the end of this talk, we will all know how we can use a simple optical fiber, the one used for communication, and transform this medium as a sensor capable of sensing different fields, different parameters over all its own length. But first of all, there is one thing that is necessary to understand when we talk about optical fiber sensor. In optical fiber sensor, the sensor is the optical fiber. Let's see how is that possible. Okay, basically, in an optical fiber, we convey light, and it is reasonable to assume that if the environment change, and when I talk about environment, I refer to any kind of physical field, temperature, strain, pressure. Well, when these things change, it is reasonable to assume that the properties of the optical fiber change. And when I talk about properties, the first things that I refer to is the refractive index. The light that propagates into the optical fiber is a function of the properties of the fiber. Therefore, if the change of the environment affects the properties of the fiber, it is reasonable to expect that the light that propagates within the fiber is affected as well. And this is the rule, this is the crucial point of optical fiber sensor, exploiting the interaction of the environment with the fiber and the interaction of the of the fiber with the light that propagates through the fiber to understand what happens outside the fiber in the environment in which the fiber itself is immersed. There is one important thing here. We are talking about physical contact sensor. We are sensing whatever is surrounding the fiber. In a broad sense, physical contact could be having the fiber immersed in a temperature field that change. In that case, the physical contact will be transferred through thermal conduction. It could be stress. You attach the fiber to a structure. You sense what happens to the structure at which the fiber is attached. So let's say that it's not like the previous talk. We are actually sensing something by touching in a very broad sense. But we will see that this technology allows us to achieve a knowledge of the fields that are much more like to that one can obtain with imaging process because of the resolution and of the accuracy. So the fiber is not the mean to convey the signal, but is the sensor itself, okay? So it's a matter of measuring light, and I think that here there are many people that are good at measuring light. Which kind of properties of light are we interested at? Well, a different kind of properties. I mean, when we talk about electromagnetic fields, we can refer to amplitude. Let me see. Okay, we can refer to amplitude, to phase, wavelength, polarization, and in the literature, you may find a lot of sensors that are based on the measurement of these different properties, because it's possible basically to relate the different properties of the electromagnetic fields through different kind of modification of the variation of the environment, such as temperature, strain, pressure, either static or dynamic, but even more fancier, actually measurement, such that, for example, magnetic field, chemicals, shape, even radiation, okay? So now we know that an optical fiber can be promoted as a sensor. There is still one thing that is missing. My talk is about distributed optical fiber sensor. That is basically using an optical fiber to sense continuously or distributedly all along its length. How is that possible? Well, the answer to this question is very simple. We may actually exploit Rayleigh scattering. Rayleigh scattering exists in many kind of different systems, and it exists also on the glass that made the fiber. Basically, due to the, let's say, inhomogeneities in the structure of the glass that made the optical fiber, the refractive index actually fluctuates a little bit. Let's say that 1 part over 10 up to the -6. That's the kind of variation we are looking at. It's a very pure and very homogeneous medium, but it has inhomogeneities. That kind of inhomogeneities determine backscattering of the light. Here, what you see is a typical setup that is called optical time domain reflectometry. That is nothing but a device that performs a radar scanning along the fiber. We launch a pulse from here. Okay, we launch a pulse from here. The pulse propagates through the fiber. Due to the scattering, some of the portion of the light is reflected back at the input. If we measure the light that is scattered back at the input of the fiber itself, we have several information. First of all, we collect the light we would like to measure. We collect light, it's a very generous term to say that because the amount of light that is collected is in the order of -100 dB per millimeter of fiber illuminated, okay? So that's the kind of measurement that we need to tackle. But we have also another information, the time at which this light has been collected. This time can be actually related to a position at which that back reflection has been generated, because it's the time that this pulse takes to reach that position and be reflected back. Basically, it's a matter of measuring the so-called round-trip propagation time. Round-trip propagation times allow us to collect the light that we are measuring at a given time to a specific position. Well, this is the very simple way in which most of the distributed optical fiber sensors work. We have an interrogator that accesses the fiber from one end. These are important things. I mean, we are accessing the fiber to one end. This is very easy. I mean, it's very convenient when you have to install this fiber. We don't need to have access to both the fiber. And relying on backscattering, we achieve also the way to convey the signal to the point along the fiber and collect back the information, and therefore to actually locate the position at which we want to perform that measurement. This can be done in a very efficient way. Up to now, there are systems that can interrogate tens of kilometers of fiber, hundreds of kilometers of fiber with a resolution of in the order of 1 meter. It means thousands of measuring points. That can be scaled up, and it can be of interest of different disciplines. We can measure tens of meters of fiber with a resolution of 1 millimeter. In this way, we have the fiber that convey the signal and get the information back from the fiber itself. Imagine to do something like that with any kind of other physical contact sensor technology. It is basically impossible. This is in the time domain. For those of you that know a little bit about control theory, what we are doing with the optical time domain reflectometry is basically the characterization of the impulse response of our system. We know well that this characterization can also be performed much more better in the frequency domain, collecting what is called the frequency response of our system. That is what is done with this additional approach. I'm not going through the detail, but basically we are obtaining an equivalent representation by performing a scanning on the frequency instead of the time. We have this duality between time and frequency, we know well. Well, it is also possible to apply the same paradigm to optical fiber sensor. We achieved what is called the optical frequency domain reflectometry. It's such good that we can perform the measurement of the back reflected field with an accuracy in the order of 10 micrometers of spatial resolution. This is not actually the resolution of the measurement, because data then has to be treated. But at the end of the story, we end up with system with millimeter resolution over many tens of meters of fiber. That can be also upgraded to perform, for example, a distributed measurement of polarization of birefringence all along the fiber that we will see in a while that has a relevant, I mean, it's important for some kind of measurement. And what else? It's very convenient, okay? So now what I would like to show you is some example. The first two are very, let's say, tough example from structural monitoring, and the other one are much more related to medical application. So the fiber is very small. It's, let's say, a thin cylinder of glass in the order of 1/8 of millimeter of diameter. Usually the cable that is used to protect the fiber makes that a little bit larger, but at the end of the story, it's it's not that invasive. It can be integrated in a lot of structure. We can take advantage of interrogation from one end, And for example, we try to integrate the optical fiber in this kind of, let's say, devices. These are called soil anchors, are nothing but nails. These are nails that we can use to actually try to secure landslides or, let's say, soil collapsing. You have position in which, I mean, we have location in which we have some problem with collapsing soil. We try to remediate by using nails. These are nothing but nails that try to grasp the soil to, let's say, much more solid inner layer, for example, of bedrock. And I mentioned that it's very small invasive, the optical fiber. So we actually instrumented one of these nails with a couple of optical fiber. What was the aim? Measure what happens once the landslide proceed and probably fall down. And just to be very short, this is the kind of measurement that we had. The distance refers to the depth at which the fiber were actually installed with the nail itself. The blue and the red curve correspond to the point at which the moment at which those fiber has been installed. What we are measuring here are the relative deformation of the fiber that is embedded within the nail. So at the end of the story, we are measuring how the nail is deforming due to the things that the landslide is proceeding. This shape, a triangular shape that show that we have high strain at the ground, are normal. It means that basically the nail is actually grabbing is actually putting force to contain the soil itself. What happens after 4 years is that the strain becomes much more larger near the bedrock. This means that the soil is trying to pulling out the nail from the bedrock itself. Okay? We can measure what happens in terms of how is proceeding the landslide and how healthy is the nail itself. Other example, we actually insert the optical fiber with a model of the landslide. This is interesting because in this case, we are trying to measure wet soil. That is nothing but soil, it's solid, but it's basically fluid. And we managed to obtain this kind of image. This is the strain field at the surface at which the sliding is occurring. It's basically an image of the field of force exerting on the surface of the sliding surface. Other example, I will go through quite rapidly, shape sensing. You may be aware that by measuring the strain in a bundle of elements, we can actually determine how a structure is bending. This is a relevant application in terms of basically endoscope, navigation of endoscope. You think of having a structure. Whatever is on the top of the natural axis is actually elongated when it bends. Whatever is below is actually reducing length. Well, we can equip this kind of structure with bundles of optical fibers, or we will see in a while a fiber with multiple cores, measuring the strain and determining what is basically the shape. It is not that easy, as I was saying, because at the end of the story, it's actually a matter of solving a problem in the so-called Fresnel frame. Measuring the strain at the end is not enough. We have also to measure the twist over the axis of the endoscope itself. And there is no way in which you can measure twist with only strain. We have to measure something else. What can we measure? Polarization. By measuring polarization, we can solve this ambiguity in the twist of the endoscope itself. And here you can see some performances. The blue curve is the real shape. The green one is the one if we use only the strain. And the red one is the one using the strain with the polarization information. The very last example, and I promise I will close, measuring birefringence is also very useful because there are some physical fields that affect birefringence, in particular circular one, that are basically magnetic induction field. Whenever we have a magnetic induction field, we can rely on the so-called Faraday effect that determines a rotation of the polarization of the field along the fiber, for example. And by exploiting this, we managed to probably measure for the first time the magnetic field with an MRI machine, a full 3D measurement, let's say a full spatial measurement of the magnetic induction with an MRI machine. I will conclude, I promise. This is the phantom that we use, wood, because of course we cannot use any other I mean, we can use metal. We can use fiber made of electric, okay? We actually end up with these 3-layer fiber that were overlapped such that we actually figure out 100 points in which we have at least 2 fiber, because we need to understand not the intensity, but also what is the direction. I mean, it's a full vectorial measurement of the magnetic fields. And this is what comes out. This is a measurement of the magnetic field inside an MRI machine over the plane of the phantom itself. No way to do that with other kind of technology. I will conclude, promise. I was asked by organizer to mention some negative results. And actually, there has been a lot of, I mean, during my career, I had a lot of problems. Wrong models, measurement affected by a lot of error. And I asked myself what was the common reason for that, because, I mean, it was worthless to just mention one of them. And I realized that this is a matter of really intrinsic with the kind of activity I'm doing. I'm working with a technology and the physics that's behind that is very transformative. And this kind of technology requires a multidisciplinary approach. We require integration of discipline, like the reason for which we are here, right? And in my case, it's a matter of, I mean, these kind of things require at least 3 expertise. It's like this 3-leg stool. There is one leg that is the physics, the technology behind. We need expertise in photonics, barely. For my kind of activity, I mean, working on the field is not like working in the lab. We need a good system integrator. That means one that knows how to deal with anchoring the fiber, which kind of coupling we are addressing. All these kind of things are not banal, believe me. And then this kind of technology produces a large amount of data, such that most of the time we don't even have the model able to actually digest that data. And this is a problem. So if one of the 3 legs is not solid or is missing, it's really a problem. And for sure, you will fail. I think that is something that is not related only to this kind of, let's say, field of investigation. So that's my message for why we fail. And I will skip the conclusion. I think that I've shown you a little bit how good optical fiber sensors are. And I would like to thank all of you for your attention, patience, and of course, all the different collaborators and mates along this year, and of course, the organizer. Thank you.